I'd like to welcome everyone to the inaugural, the first ever EarthSystemData podcast, which is the first of many, I hope, and I hope they'll all be as topical and as interesting as this one. Just a couple of introductions then. My name's Dr. Craig Wallace. I'm a climate scientist and ex-senior research scientist from the UEA's Climatic Research Unit, but I'm the founder of EarthSystemData, and EarthSystemData is a data analysis company for climate science, but also an outreach organization as well. We're passionate about talking about climate science and disseminating knowledge where we can, and it gives me great pleasure for our first guest to have Dr. Richard Hall from the University of Bristol. And it's a name you may well be familiar with, given all of the press in the last 10 days or couple of weeks or so about the beast from the east and the phenomenon known as sudden stratospheric warming up in the high atmosphere. And Richard is lead author on a recent publication that backs some of the research behind this phenomenon. The timing couldn't have been better, and it's phenomenal to have Richard here to chat about the topic. So welcome, Richard. How are you?
Hi, Craig. I'm fine. Thanks very much for having me. I'm looking forward to talking to you.
Great stuff. As I say, the timing couldn't be better. Just as a kind of a quick question to get going, which kind of sets the scene here. It's a little bit off topic, but how did you get into, firstly, science, and how did you firstly get into this particular line of sort of climate and meteorology up in the high atmosphere?
Well, I haven't actually been in academia for that long. I was actually a school teacher for most of my career, but I did geography a while back, and I've always been really interested in the Earth and how it works. And so a few years ago now, I was having these wonderings about whether I could go back into academia and whether my brain would still work along those lines. So I took a year out of teaching and did a master's in polar and alpine change at the University of Sheffield. And at that time, I suppose, I was more sort of interested in glaciers and ice, but actually part of that was climate. And subsequently, I just absolutely loved it. And we went on a month's field trip up to the Arctic, and it was absolutely brilliant. And I just decided at that point that actually, yes, it was time for a career change and to go back into sort of my first love, if you like, of Earth science. And I then did a PhD on jet stream variability at the University of Sheffield.
Right.
Now, that included a little bit of stuff about the stratosphere, but not a vast amount. But I was always sort of quite interested in the stratosphere as a possible sort of influence on the jet stream, particularly in winter.
What would be good was if we talk a little bit in a moment about what a sudden stratospheric warming event is and how it kind of ends up being referred to as a beast event or a beast from the east. But just for the benefit, I think quite a lot of people who might end up watching this might not have a great grasp of kind of the vertical structure of the atmosphere that, of course, we all live in at the bottom. And if we could maybe run a quick description of how at the bottom we've got quite high pressure because there's a lot of air on top of us. But if you get up to, I always think maybe about 10 kilometers or 12 kilometers, you might put a lid on that as where the weather is. And then above that is a different kind of dynamics that the planet operates and known as a stratosphere. Would you say probably about 12 kilometers height as a designation between the two?
Yeah, that's right. I mean, the stratosphere I always think of as being sort of around about 10 to 50 kilometers, but it does obviously vary slightly, depending on whether you're sort of nearer to the equator or nearer to the pole. But that's right, yeah, and it, obviously the pressure in the stratosphere continues to decrease with height, but one of the interesting features is that the temperature actually increases with height in the stratosphere, so it's very sort of stable, stratified, hence the name stratosphere.
At height, that heat, if I'm right, is a result of chemical processes.
That's right. It's ozone and absorption of the solar radiation in the stratosphere, and the ozone concentrations are higher in the stratosphere, and so you get that absorption and converted into the temperature. Yeah.
Just to kind of help us with the conversation, I'm just going to share a picture here of the general circulation of the planet within the troposphere. So this kind of low-level circulation of the atmosphere. If you just bear with me, let me see. So this picture for what we've just described as the troposphere, so this lower kind of 12 or 10 kilometers of the atmosphere. Let me zoom in here. Can you see that okay, Richard?
I can see that fine, yeah.
Great. The reason I just wanted to show this quickly was because it shows from the equator, where the biggest energy obviously hits the planet, it sets up these heating cells whereby air rises, and as you know, just for the benefit of our viewers, the air moves north, cools, and then it comes back down to the surface, and there's another one of these cells up here. First one is a Hadley cell, second one's the Ferrel cell, and then we've got these right at the top, we have these polar cells, and these interfaces here between the two give rise, at least at the surface, to a westerly circulation. Would you agree there? The polar front would give us the westerly.
Yeah, that's right. Yeah.
And so is that, but my understanding of how this also operates in the stratosphere, particularly in winter, the normal conditions are for a westerly circulation also around the polar cap. Is that right?
Yeah, I mean, the stratosphere is quite interesting because the circulation in summer and winter is completely different. So in winter, if you think about the stratosphere and the North Pole, let's just take the northern hemisphere for the moment. The North Pole is obviously sort of tilted away from the sun, and so is in 24-hour darkness. Whereas towards the equator, there's obviously quite a bit of incoming solar radiation. So you get a very strong polewards temperature gradient in the stratosphere. Relatively warm at the equator to very, very cold at the pole. And so you can think of this sort of cold air sitting over the pole. And because of that temperature gradient, you then get these very strong westerlies blowing around the cold air, which is known as the stratospheric polar vortex. And that develops every winter in pretty much the same way, perhaps say from November onwards, is retained through the winter, and then breaks down sometime around about April. And then
coinciding with the reappearance of the sun and the warming of
that's right, and breaks down in sort of April time, and then you actually get easterlies in the stratosphere. And it's that winter time when you've got the westerly winds and the polar vortex, excuse me, that's when the stratosphere can actually link with the lower level of the atmosphere, the troposphere, and hence our interest in these sudden stratospheric warmings.
So one question you might be able to answer, Richard, that I was thinking about is so you've just described this polar night jet westerly big circulation enveloping the polar regions, but to what extent, if any, in the stratosphere is this 3-cell structure replicated? If at all?
Yeah, I mean, it isn't, because the lids of those 3 cells are basically at about what we call the tropopause, the sort of the boundary between the troposphere and the stratosphere. There is a sort of a slower circulation in the stratosphere going from the equator to the pole, called the Brewer-Dobson circulation. I mean, that doesn't really sort of concern the sort of sudden warmings particularly, but there is a sort of an overturning circulation, but it's much more slow, far less dynamic. The polar vortex is driven by the temperature gradients.
So it's like people may have heard of the thermal wind.
That would be
so. So just almost like one cell kind of thing, broadly speaking. Therefore, it must be easy to study, right?
Yes, well, quite. I mean, the problem is that data on the stratosphere has been relatively sparse until more recently. So, I mean, the sudden warming events that we're going to talk a little bit more about have only really been, well, I think they were first discovered in about 1953 by a German scientist who noticed a strange warming at high levels by sending up, I think, one of these balloons or something like that. And so we only really have records of them for about 60 years or so. Although, we think of them as a natural sort of fluctuation in the atmosphere, and so have been going on for much, much longer, but we only know of this period of time where we have records for them.
This is great. We're getting into what the phenomena actually is, and from my reading and understanding, which I'll put to you for elaboration. And one critical criteria is that at a certain at a certain high pressure level, high altitude pressure level, where the pressure is low, the ordinarily westerly circulation has to reverse. And along with that, there's a rise in the temperature at that pressure level as well. And if those two conditions are met, would you say that's what you would call a sudden stratospheric?
There are slightly different definitions, but I think the most accepted definition of a sudden warming event is that wind reversal at a certain altitude and at a certain latitude as well. So it's 60 degrees north, and it's at about 10 millibars in the atmosphere. And it's an average wind reversal. It doesn't mean there's a sort of universal reversal of the wind. So if you put the average wind direction around 60 degree north, the average would reverse, but in parts it could still be westerlies. Yeah.
And you made a great point about availability of data to actually diagnose when these things are happening. And I noted one sentence in your paper where I think you said one study had estimated perhaps as 6 of these a decade. And obviously one thing to, I guess, consider is how useful are satellite, you mentioned radio sonde balloons going high into the atmosphere to sample the conditions up there, but have recent satellite measurements then supplemented that style of observation to make these things more detectable?
That's right, yeah. I mean, we think of 1979 onwards as being what we know as the satellite era. And so, there's an increasing amount of data there from satellite observations. Now, for example, something like wind speed isn't a direct observation, but it can be inferred from the data that the satellite may collect about temperatures and so on. Before that, the data is really reliant on, I suppose, the radio sonde balloons and maybe aircraft flying at higher levels or some such. So we have evidence of sudden warmings from the sort of late 1950s to the 1979. And there are a number of events, but I suppose our most reliable data comes from 1979 onwards.
One thing that I myself have kept my eye on, just to kind of summarize what we're seeing here, as you all know, Richard, but for the benefit of our viewers, we have the temperature over the North Pole at a particular pressure level. This is 30 hectopascals, which I've taken to be about 30 kilometers up in the atmosphere approximately, or 29,000 meters there or thereabouts over the North Pole. And this thin black line is what you would expect during the course of a year. And then this black line is the current observations. And this sudden warming, the temperatures are low, but obviously by, I think this was the first week in January, they spiked and they got really, really high. And so it's gone from like minus 80 up to, I guess, minus 40, negative 45. So this temperature rise then, Richard, is this because the cold blob of air has gone somewhere else and there's warmer air coming in to take its place, or is that not the case at that, or is it something else at that altitude?
Yeah, I think you can think of it like that, because the sort of the normal vortex tends to be located, sort of nearly over the pole at sort of fairly high latitudes. But yes, it can either split into two smaller vortices, in which case those two smaller vortices tend to move apart, and so therefore you will be getting that warmer air in between them, or it can be displaced, shifted to one side, and therefore the area over the pole tends to get warmer, and that cold air has slipped sideways.
Well, one thing that occurred to me, Richard, I actually have the plot as well for this is 2018, the de facto beast from the east, and again we can see this big warming event slightly later in the year, February. But prior to that, there was kind of this increased variability and a dip in temperatures. And one thing, which is probably highly dangerous to do from a scientific standpoint, but nonetheless it did occur to me, was that in this event as well, there was a cooling preceding the warming. Is there any dynamical or any... Do you have any grasps or kind of inkling about whether that's a precursor to the warming?
To be honest, we haven't really looked at that. And I think, like you say, there does appear to be something there. But if you look at that curve, the thin curve on your on the screen is the sort of average over all events. But each individual year is actually quite noisy, and there are quite a lot of just random fluctuations. And I think you would see that sort of magnitude of fluctuation, temperature change most years, whether or not there's a sudden warming. So I wouldn't like to.
That's the answer. That's the answer I would give as well. So one obvious question that also springs to mind, and I think you cited a couple of studies in your paper, was the initiation for these events. It's not impossible that at the surface of the planet over the kind of the subarctic areas, it's not impossible that the circulation, or the wave-like structure of the circulation in a year, it's not impossible, is it? And give me your thoughts on this, that can actually rise up through the atmosphere and then hit the stratosphere, and then through a process known as resonance, combine with the high altitude wave structure to an extent that the resonance between the two then deconstructs the polar vortex and causes it to split. Is that possible?
Yeah, I mean, yes, you tend to get these sort of wave patterns in the atmosphere, particularly in the northern hemisphere, because you've got land-sea contrasts in temperature. So you do tend to get a sort of a sort of slightly more wavy flow, whereas in the southern hemisphere you've got the Antarctic and surrounded by sea, and you don't get that sort of wavy pattern. And so if that wave pattern, if you like, is amplified at the surface for any reason, then it has the potential to sort of move upwards vertically, and it can disrupt the stronger winds blowing around the vortex. It's called wave breaking, so it's like waves breaking on a beach. You get that sort of overturning of the wave, and there are different theories about how it actually works. But essentially, you might be able to think of it as like drag on the winds, and a slowing down and a disruption of that vortex. So yes, it's this sort of wave propagation from lower down is shown to link with variations in the stratospheric polar vortex.
See, I think that's a really fascinating aspect, and also as these types of events become more possible to identify, one obvious thing that struck me was that if for some reason, for example, at the surface around the Arctic and the subarctic, which we know is a rapidly warming area due to carbon forcing, if that affects things like local snow cover, which may impart the local wave pattern of circulation, and this is probably another question you might want to skip on, but feel free to give me your thoughts. If via carbon forced climate change, that surface circulation gets changed even more so than today, then if there's a connection from the surface up to the top that can cause SSWs, then it strikes me that one thing to do would be to, you kind of allude to it in your paper, you say your method of identification can be applied to the climate models that are used to predict the future. Then I think one neat thing to do would obviously be to analyze the future projections and see if the frequency of SSWs goes up. I mean, that must be something you've thought about yourself.
Yeah, I mean, there's a lot in that question. First of all, I suppose a lot of the sort of wave driving can be seen as coming from the tropics. So El Nino is a sort of major contribution to the strength of the polar vortex, or not. Also, if you've got areas of particularly strong convection in the tropics, which can sort of move around the tropics, it's known as the Madden-Julian oscillation, but I guess we probably don't need to get into that too much. But that can set up these sort of planetary wave patterns, which can propagate sort of polewards and upwards, and can have an effect on the vortex.
So in a El Nino year, when El Nino is strong, what's the effect on the polar vortex? Is it stronger? Well, is it more stable? Or?
It's interesting because when I looked at this year's polar vortex in sort of November, early December, it was a fairly strong vortex, and I would have said it looks unlikely that we'd get a sudden warming this winter. And partly that's due to the sort of the preconditioning, if you like, from things like El Nino, because this year it's actually La Nina.
Right. I was going to say we're in a La Nina phase where.
Yeah, and that has a sort of a strengthening impact on the vortex.
Okay.
So therefore, perhaps making sudden warmings less likely. There's another phenomenon as well in the equatorial stratosphere known as a bit of a mouthful, the quasi-biennial oscillation, or the QBO, which is basically, you can think of it as a sort of a reversal of the stratospheric winds every 27 or 28 months. And you can think of them as going westerly, and then easterly, and westerly, and easterly. And when that's in a westerly phase, it's moving in the same direction as the polar vortex winds, and it strengthens the polar vortex. Whereas if it's easterly, then it can have a weakening effect. And this year, again, it was westerly, so again, a stronger vortex. So the sort of tropical influences this year are all pointing towards a stronger vortex, which is what we saw. Wow. So in one sense, the sudden warming was quite unexpected. But you make an interesting point about the Arctic influence. And I mean, there have been a few papers which look at the Arctic influence. And an area of particular interest, I think, is probably the Barents-Kara Sea region, which is off the north coast of Siberia, around Svalbard, actually. And this summer has been particularly interesting up there because the sea ice has retreated a lot on that side of the Arctic and remained at persistently low levels well into autumn over that region. And we also had warming, very high temperatures in Siberia last summer, if you recall, as well. There is an open question as to whether there's a sort of contribution to the sudden warming from...
This is the Kara Sea region here.
Yeah, that's right. Whether there's a sort of a contribution to the sudden warming from a sort of positive temperature anomalies over that region, which is... Yeah, like I say, it's an open question, because the other interesting thing about that region is it lies in exactly the right place to cause constructive interference with the planetary wave patterns. So if you get waves in phase with each other, so the crests are at the same point, then it amplifies the magnitude of the wave. Whereas if the crests are in different places out of phase, then it can damp down the wave, and the Barents-Kara Sea region is exactly the place to amplify the wave patterns. And so it is an interesting question as to whether there's a contribution there, but it could be actually more a case of the Arctic, if you like, modulating or regulating a signal which is coming from, say, high pressure over the Ural region, which sort of sets up a flow into the Arctic. And then if the Arctic's already warm, again, that can be it's a sort of bit of a chicken and egg with the Arctic. Sometimes.
It just struck me as something, as you pointed out, to the Siberian warming this year. And it seems every year that because of the local processes over northern Russia, where it's usually permafrost, and the permafrost is going, and then there's gases that come out of the permafrost which locally feed back and cause more warming. But if there is what we might call a teleconnection between this and other processes, then it doesn't bode. It doesn't take much to think, hang on a minute, this doesn't bode well. We should be worried about what we're doing anyway. But could this emerge as something that really ought to worry? It's a stark, tangible, noticeable effect, possibly. And I guess as people apply the work that you've done in your paper to the climate models for the future, that kind of stuff might come out, right?
The jury is out at the moment in climate models as to whether sudden warmings increase in frequency or not. Because basically there was some work done on this, and you're basically getting some models saying there's going to be an increase, some models saying there's going to be a decrease, and if you pool them all together to get this sort of ensemble mean, there's no change.
An increase in the frequency of SSWs.
Yes, that's right. So at the moment, there doesn't appear to be the sort of evidence there. But it could be a deficiency in the models, because obviously they're showing an incredibly wide spread from increasing to decreasing, and the question is, well, why is that? What is it about the models that they're not capturing? Because there are discrepancies between model representation of sudden stratospheric warmings and the observed.
So this is quite a good point, just to point out to some of our viewers the way a climate model will solve equations at certain levels through the atmosphere up to a point. And I guess some climate models, just through design, don't solve equations high enough perhaps to embody the processes that cause SSWs, and some climate models will. Is that right? Is there a difference?
That's right. And I think, probably over the last 10 years or so, there's been a significant improvement in the sort of the vertical resolution of models. So it's the number of levels, the number of slices, if you like, that the models are sort of calculating values for, but also what we call the lid height of the model, where it actually stops. And the lid height is increased, and that sort of resolution up to the lid height is also increasing.
Well, what's a typical top? So as we go up through the atmosphere, pressure decreases because there's less air in that. So in a typical kind of climate model, what would be the top levels pressure, do you think?
I mean, quite a lot of them are probably to about 60 to 85 kilometers now, so it's pretty high. Yeah. I mean, some of them.
So what would that be, about 10 hectopascals?
No, it's less than that. It's about 0.001 or something. I mean, it is really.
It's almost space, right?
Yeah, you're up into the next layer of the atmosphere. I mean, I have actually done some work on this, which is sort of ongoing and it's not published. But there are a couple of. We sort of looked at a group of the latest climate models, and the ones that were struggling the most had a top that was only just at the top of the stratosphere, or actually below the top of the stratosphere, and they were certainly less good at representing the stratospheric sudden warmings than the ones with the sort of higher top. So I think we may have gone, the top may be high enough, and the resolution may be high enough, but there can still be processes that aren't very well represented in the models. So I mean, this is the project I'm involved with, and I don't really. Some other people are doing this, but there are there are things called gravity waves, which can also propagate up into the atmosphere, and I suppose you can sometimes see those in clouds where the wind has gone over the mountain, and you can see a sort of a wave-like pattern in the clouds.
Yeah, you can see them clouds, no clouds, clouds, no clouds. Yeah.
But the gravity waves can propagate up into the stratosphere, but it's not represented at all. They have to use what they call parameterization, so sort of feeding in quantities, if you like, to represent gravity waves rather than actually representing the processes. And it could be that they're sort of particularly, and you've got different ways of doing that in the models.
Yeah.
And so I think that may well account for some of these quite large discrepancies, failures to portray things in a way we would hope.
Just to rewind a little bit, Richard, one chart. Well, first, actually, let me ask a question. Actually, quite a cool question I was going to ask was, I think your paper was, just to summarise, and I'll let you elaborate, that your paper designs a technique to identify sudden stratospheric warming right from the top through the atmosphere. And I'll let you say a little bit more about that. But my question was, the paper got accepted for publication, I think was it maybe around December the 20th or just before Christmas. And then, actually, funnily enough, I remember looking at the JMA plots for the temperature around Christmas, thinking, there's not much going on. But then by January the 2nd, 3rd, when this warming spike went up, and I thought, was the acceptance of your paper, did you have an inkling that something was going to happen and you thought, well, we'll submit the paper now, or was it just the way the stars aligned?
It was entirely fortuitous.
That's astonishing. It really is.
Yeah, because the work was obviously done sort of during the course of last summer, largely, and it's just a case of we completed the work, submitted it, and you always have a few revisions and things like that to do, and it just happened to get accepted at bang on the right time.
I'll just say, I'll put a link to the paper in the description of the podcast when I've edited, and also just to say, Richard, that I don't very often print out papers these days. I usually read the PDFs, but yours got a print. So it's the only one I've printed maybe for I don't know, maybe a few months. So there we go. That's quite an accolade. But the second question I had then was, having devised this technique, you and your co-authors, to identify the sudden stratospheric warming at different levels in the atmosphere, this is probably one thing I guess you're looking at, and you might go for extra funding. So by all means, moderate your answer as you wish. But have you, or will you deploy the algorithm with forecasting centres to build it into operationally?
Yeah, it's a good question actually, and it's one somebody asked me. It's deployment operationally is problematic because, in essence, you can only do a certain amount of analysis of the SSWs with hindsight when you've got the sort of data from before and after the onset date, because at the moment the event is still unfolding. So I wouldn't necessarily be able to run our algorithm from onset to surface because we don't actually know.
If I may, one question then, and just a bit of background of how weather forecasts are made for our viewers. In order to run the equations forward, each point on the planet needs an initial condition to start the forecast. And in order to provide that starting set, then all the observations go in and computer simulations can fill in the blank to produce this product, as you know, a reanalysis product. So those are produced daily in order to launch forecasts. So would it be possible to harness those daily products and then point your algorithm at those to provide some kind of real-time identification, or is that wishful thinking?
I think at the moment it's probably a bit early, because I think, take a step back for a minute, I think the key thing that we've tried to do is more specifically identify the lag time between the onset of the sudden warming up in the stratosphere and the surface impact, how long does that take?
Okay.
Because there's quite a wide range. So if you think of the beast from the east in 2018, the sudden warming was, I think, something like the 12th of February. And here in the UK, we probably noticed the impact of that round about the beginning of March. So it's around about a 2-week lag.
Yeah.
Now, some sudden warmings have a relatively short lag, and other ones have a longer lag. And that's shown in the paper. And in the past, I think what papers have tended to do is they've tended to look at the average effects of sudden warmings on the surface in a window, say 30 to 40 days after onset.
Mm-hmm.
But if you imagine those sudden warmings are all coming down at different points within that window, then the signal is going to get weakened. It's going to get smoothed out, if you like.
Different points through time.
Yeah, so what we try to do is align them on the surface impact point rather than the onset time, so you can more clearly differentiate between sudden warmings. Now, some sudden warmings have, lags of, 1 week, maybe 2 weeks. Others are going up to 3 to 4 weeks. And we found that, I think we mentioned earlier in our talking, that the vortex can split into two, mm-hmm. or it can be displaced sideways. And from an admittedly small sample, it seems as though the split events perhaps propagate downwards a little bit more quickly, but also have stronger surface impacts, certainly in the European region. Now, I think one of the ways ahead with this is to say, right, now start to look at, can we identify the factors that contribute to these different lag times? So it might be a case of, well, it's a split and a displacement, but there are probably other factors as well. So it could be to do with, surface conditions, which influence the downwards propagation. It could be, there could be a solar signal in there. There could be all sorts of things. And if we can better identify what are the contributing factors to the lag, then that is directly usable in the forecast, because we've got the onset date. Yeah. We can look at the conditions of the contributory factors, mm-hmm. and then you might say, well, we think there is a 70% probability that this will propagate downwards.
I was going to say
in a week to 10 days.
The current thinking is probably around 60% of the time that these things touch down to the surface. Is that about right? And we get a surface easterly that brings cold air. Or is that
that's probably right. So of the events, you get about 6 a decade, of which 2/3 have a detectable surface impact.
Right.
So then given that, how can we differentiate those? And I think it would be really useful to be able to say, because when the warming was identified last week, there's no indication, no way of knowing when it might actually reach the surface. Now, the forecasts are starting to suggest it could be sort of next week.
Mm-hmm. The current pockets of cold air that are influencing the UK, I to my mind from reading the charts, are just regular kind of winter systems coming through, and they've got cold air tucked behind them, and and that's distinctly different on the surface from a beast from the east, which by name is a steady airflow from the east, and in our case it's coming from Siberia, Russia, and that just locks in, right? And
that's right. I mean, these are sort of, I would say over the last couple of weeks, it's been colder. But that's not related to the sudden warming event.
Right. Yeah.
The touchdown, if you like, might be, there's a possible influence maybe this weekend, but certainly by looking into next week. But this has only evolved through time with as the forecasting point moves forwards. But, I think our technique of what's the likelihood of a particular length of lag, once we know the onset date, by looking at the factors that contribute to the lag time, could be really useful for enhancing that forecast, particularly if it's going to be a short-term impact, which the models may struggle to sort of forecast with sufficient warning, if you like.
So that's great, because I wanted to spend a little bit about your thoughts on the current conditions. And one thing it's funny. When my friends, you probably get this as well. When my friends find out what you do for a living, if it's in climate science, then they automatically think you're also an expert on day-to-day weather forecasting.
Yeah.
And I have to point out that I'm not. But you can, I can read a chart. I can read pressure levels, and to a certain extent have a comprehension of the dynamics and so forth. But and as we always say, weather makes climate, and from your research background and also from the stuff I did for my PhD, there's an understanding there. But long story short, I keep an eye on the charts, surface level and upper level, to see what's going on. This is NOAA global forecasting system, and I took this 2 days ago, and it's 500 hectopascal thickness, I think, issued on the 9th. And this kind of circulation pattern, I've annotated it with arrows, which is the mean circulation of the steering airflow, I guess. Just for orientation, here's, if you can see Britain, it's just tucked in between these two arrows here, and we've got Siberia over here, and we have this cyclonic circulation coming around here, associated with winter systems passing through to my eye. But also there's this kind of easterly flow up here. This is just Scandinavia, there's Sweden, Norway, and then Siberia over here. We've got this eastern feature. Could this, the forecasts that I checked today, which is the 13th, they actually have the westerly flow winning the battle, I guess, between this easterly flow. But is this, could this kind of be the initial signs of a touchdown, perhaps, this easterly flow over here, which I put with a question mark?
Yeah. This is the problem, because I always think where we're located is very interesting in many ways, but also frustrating, because we're sort of on the edge of so many things, and subtle changes or subtle shifts can make a big difference in terms of, what weather we actually get. Is that sort of cold, if you look on a map now, you can see cold temperatures over Siberia. Are they going to stretch far enough eastwards, or are they not going to quite make it? And I think you're right, we probably do need a sort of the establishment of some sort of higher pressure up there over Scandinavia, perhaps, to develop some sort of anticyclonic flow, which would then sort of draw the air eastwards over the UK. And there are some, I have seen suggestions that may well happen. But obviously the further ahead you go with, the forecasts are good for, out for about 10 days. But obviously the further ahead you go, there's decreasing confidence in those forecasts.
And is the, sorry Richard, I was just going to ask, is the current event you made a distinction between a displacement where the whole vortex moves, and then a split where it partitions into two, or is it just two or three? Can there be three separate entities?
Yeah, it's usually two.
And is that the event at the moment? Is it a split event?
Well, the event at the moment is slightly confusing, because it was initially looking very much like a split event, because you basically, for the split event, you get the sort of elongation of the vortex into an ellipse, and then it's sort of dividing in the middle. But then it reverted to more of a displacement pattern, and then the model forecasts are more predicting, some of them are predicting more of a split, perhaps next week. So it looks as though it might be fluctuating between the two.
Interesting.
But yeah, that's that's fairly clear at the moment.
Sorry, carry on.
You can see the vortex, the sort of centre, if you like, is over Scandinavia at the moment. And it's very clearly shifted to one side, and it is a bit elongated. But I think, running that forward into next week, some models are predicting that sort of rather banana-shaped bit in the middle may well sort of divide into two bits and drift apart. But it's not there isn't a consensus amongst models about that.
Yeah, it's interesting. This is from University of Wyoming, do some great upper level charts. This is 10 hectopascal height, So I guess up at 30 kilometers, 30,000 meters.
Yeah,
right,
that's a good level to use. Yeah.
Right. Would that be the one 10 rather than 30? I've noticed people using 2. But
10 is the usual level to use in the definition of the sun warming. So that's the level at which the winds are examined. You know, you're looking for wind reversal at 10 hectopascal.
Well, so this was from, I think, last night. I had a look, and just to get your orientation, here's green. I don't know if you can see my cursor, but
yeah.
This area is obviously, here's Greenland for the viewers. Down here is Britain, and these blue lines are the height of that pressure level. And I've marked H where the pressure level is higher, and I've marked L where the pressure level is lower. And on my understanding, is because the atmospheric column is colder, and so it's more constricted. And so at this pressure level, the way that the winds work, it would adopt annotated this arrow, this kind of easterly interjection. And I was thinking, well, if it's a split event, is this cold pool of air that's just sitting north and it's sitting over Scandinavia, could that be is that one of the polar vortex blobs coming off?
No, I mean,
okay.
That's it in its entirety.
Sorry, this is the entire
vortex.
It is sitting. Wow. So I guess if you're right up in Inverness or Wick in Scotland, if you were to look up, the vortex has literally just 30,000 meters above you.
I mean, there is a slight caveat, because actually, if you go down at different levels, the vortex can be sort of located in a different place. So
sure,
the vortex isn't a sort of vertical column.
Yeah. So it's not just a okay. So it could be shaped one direction and then come back.
But that particular level of the vortex that's where it's located at the moment. Yeah.
So this is it, just south of Greenland.
Because earlier on there was some sort of subdivision that sort of recoalesced, formed that sort of banana shape. And then I think if you there's a good site called Stratobserve. Have you come across Stratobserve?
I haven't, but it sounds great. I'll be checking it out.
You can run it forwards and you can see how it's projected to evolve over time.
Let me see if I can grab that, Richard. Sorry, Stratobserve.
Stratobserve.com. It's all one word. Yeah. If we click on maps, so let's just look at temperature and the pressure level. So
here we go.
10 hectopascals, which is effectively what you were showing earlier.
Yeah.
And then if you run through these sort of time boxes at the top, you can see that banana starts to elongate and is potentially splitting into 2 smaller vortices a little bit further ahead.
And just for orientation then, so we're looking down on the pole, and
pole's here, and
Britain's just down there, is it?
Greenwich meridian.
Oh, great.
So UK is here, and this is over Siberia.
Brilliant.
Another one, I mean, again, this is to do with how elliptical it is, but this allows you to see the sort of an ensemble of models. So that's where the models are all this is where all the models are showing the vortex in essentially the same place, and its center located here, because this is near time. But as we run forward, you see that the models start to diverge.
Right.
And you can see there that there is one of them split, a lot of them haven't. And there's a little counter at the bottom which tells you where the center is and how the vortices are splitting.
That's awesome.
How many of them are split and so on. So, you can see that as you go further ahead, there's increased uncertainty about where the vortex is actually going to be and whether it's going to be split or displaced or what have you. And I'll show you one more thing on here which is interesting, this is akin to what we've been using. So this is a time along here. So this is the sort of American way of doing dates.
So it's day then.
Dates along here and pressure level here, averaged over the northern hemisphere, and you can see the wind reversal there. But perhaps the most interesting one from
so the colours are wind speed as a westerly. So if it's green, it's 60 meters a second westerly, and then this orange here,
and that's where the wind's reversed at 60 degrees north. So this is all at 60 degrees north, taken for every day, up to the present here, and then forecast ahead. And then if we do this one, this is the sort of annular mode index, the sort of like the northern annular mode, which is a bit like the NAO. And there you can see and now this is what we use to track our sudden warmings in the paper, something very similar to this. So you can see the pointer here. Here's the sudden warming coming down and then extending across here. Now you could argue that the first surface impact is here, where there's a sort of perhaps a slightly weaker blue surface impact. Blue is a negative annular mode, which we would associate with colder weather over Europe. But maybe this is the stronger signal here, towards the end of next week, where we may be getting more of an impact here. But you can see the sort of forecast line is gradually shifting forwards here, and it's becoming more reality. And you can sort of check on the progress, but it is indicating that we can expect some sort of surface impact with this event.
Wow.
In the next sort of 10 days or so.
That's great. That's fascinating. It really is. It's not a sight I'd seen before, Richard. That's phenomenal. And I guess if things were to touch down next week, what would that be? About a 22 day lag between.
That's right. You're looking at the 5th of January to maybe the 25th. So 20 days. So longer than some.
but plenty of time to buy some gloves.
But that's the useful thing, because if we're able to predict that lag or give a probability of that lag, it gives advance warning to people who may want to know. So it's useful for infrastructure planners. Is it going to impact on transport? Do we need to get the gritters out? Power, energy generation is also interesting because. So I think people may remember that I think recently, just before Christmas, the UK had some days where 100% of the energy is contributed by renewable farms. Now that's because we had strong westerlies. However, with a sudden warming, you can envisage a situation perhaps where energy demand increases because of the cold, but the supply from wind power may actually drop because the easterlies are not as strong as the westerlies. So again, a sort of prediction here, would help some contingency planning, for energy supply and so on. Shall I stop screen sharing now?
If you that's brilliant. Go for it, Richard. That's a really useful site. But one thing that also people might be thinking about is in the summer, when we get heat wave conditions especially in Britain, it's often accompanied by a high pressure system sitting over the country that often draws in an easterly airflow from Russia, which happens in summer to be very, very hot and in winter very, very cold. But the mechanics of how that circulation pattern appears in the summer must be radically different. The upper air circulation, there's no wintertime polar vortex. There is a polar vortex, but it's not very pronounced, right?
It's not there. It just isn't there.
It's not there. Okay.
And so in the summer, there's no interaction between the troposphere and the stratosphere. Any sort of wave patterns can't propagate upwards because a planetary wave can't propagate into easterly winds at higher level.
That's great. It's brilliant. So I'm just looking through my notes, Richard, and I think all the questions I had to mind, I think we've covered. I think we've done a great kind of in-depth overview of the beast and the SSW behind it. Did you want to actually, having been a postdoc myself, would you like to acknowledge your funders?
I will do, yeah. Well, I'm funded by NERC, the Natural Environmental Research Council.
Okay.
And they're funding this project, which is a joint project, between Bristol and the University of Bath and UCL in London. So different people are doing different components of the project, which is all about the impact of planetary waves and gravity waves on the stratosphere. But our particular focus in Bristol is this sort of impact on the surface and links to extreme weather.
And does the project have a homepage? I can put that in the description below.
I'm not sure it does, actually.
Okay, I can have a look as well. So some do. I know NERC definitely does, so we can link to NERC. That's great, Richard. And just before we wrap up, a couple of fun questions. We spoke about your how you got into science and research from your journey, which is great because it wasn't an ordinary one. You've done teaching and that. But was there? Here's a question: was there a particular thing, perhaps, like when even recently or when you were younger, that really brought you to geography and meteorology, and then into climate science and the general circulation of the atmosphere? Yeah. Was it a general interest in the weather, or was there one thing you thought, wow, this,
Right. And the geography is easier than the climate and weather because I've always loved mountains, and when I was young we always used to go as a family to the lake.
Good choice. Oh, beautiful. Yeah.
And we spent sort of two or three times a year we were up in the Lake District. So I love mountains. And then when we progressed at school and I found out about glaciers and how this landscape had been carved by the glaciers, then that made a real connection with me emotionally, if you like, with geography.
Yeah.
And so I've always then had this interest in the world and how it works. The climate bit really only came out of the. I've always had an interest in the climate, but a more specific interest really only came out of the Polar and Alpine Change Masters that I mentioned earlier. Where I was really fascinated to see, about how the climate was changing over the Arctic and how that may potentially have an impact on, say, the jet stream over the mid-latitudes and so on. And it was really through that. So it was a bit unexpected, the climate part of it,
right.
But none the worse for that. I'm glad that I didn't sort of close things down and just focus on, say, glaciers.
Right, but it's a great starting point. And when I speak to people who study geography, it's usually glaciers that everyone remembers what a moraine is. But then if you go to the lakes and also into Scotland and you see these features, and then if you go online and you search for historical maps of where the ice sheets used to sit, and they were like right over the North Sea, even down into bits of Norfolk, and then obviously over the lakes and Scotland, and you wind your mind back, a few 10,000 years, tens of thousands of years, and you think that, wow, this was, it's not make believe, it actually happened. That as a gateway into.
That's right.
This line of work, I think, is pretty powerful.
Yeah.
Final question, and then we'll let you go, Richard. Favorite scientist? Do you have one? You can't nominate your co-authors.
No. That's a tricky one. Well, Brian Hoskins has been very influential over the years, his thinking, and he's still active now, even though he's, I think, probably officially retired, but, he's been influential on an awful lot of people in the sort of climate dynamics field.
And he's a Sir now, right?
He is Sir Brian, yes, that's right.
Brian Hoskins.
Right. He is somebody who I admire greatly, and I've had the pleasure of working with people like Tim Wollings in Oxford.
Great. Hi Tim, if you're watching.
And Adam Scaife at the Met Office is another great scientist with whom I've worked, and are obviously very influential in their field. So they're perhaps the sort of the next generation of atmospheric scientists. Great
answer. Really interesting. So that's brilliant, Richard. It's been fascinating, and thanks for staying. We've run over the hour, so thank you very much indeed for doing that. One thing we'd like to do at Earth System Data is we'd like to make a small contribution to charity to say thank you for your time. So I'll get in touch with you after the show about that. And if you have a think, if there's someone or something close to your heart charity-wise,
that's great.
We'd like to do that. And the podcast will be back. There'll be a second episode, and it will be a hard one to follow, but we have some ideas about a subsequent guest. But all that remains for me to do now is to say thanks everyone for watching, but also most importantly to say thanks to Richard for his time. I'm sure he's got more press to do, and we'll be watching the charts in the next week or so. So it's a fascinating topic, Richard. Well done on the publication again. We'll put a link in the show description for that. So thank you very much indeed.
Okay, that's great. Well, thanks ever so much for having me. It's been a pleasure.
You're welcome.